Okay, let's tackle another example problem. In this case, we're looking at two boxes that are stacked on top of each other and sliding together to the right across a table. Each of these boxes has its own mass, and there's going to be kinetic friction between the bottom block and the table, and static friction between the two blocks themselves. And what we want to know is what the maximum tension force we can apply to that bottom box is so that the boxes will continue to move together. And we want to know what happens if that applied tension exceeds the maximum value that we find. So the first thing we want to do when starting a problem like this is ask, does the question that the problem's asking us actually make sense? So in this case, why is it asking us about a maximum tension? Why not a minimum tension? Well, let's think about it. If the tension is really large on that bottom block, it's going to try to make that bottom block accelerate very rapidly. And if they're going to continue sliding together, they're going to need to have the same acceleration. But looking at the top block, what's the only force that could supply a acceleration in that horizontal direction to the right? Well, as we're going to see, it's going to be a static friction force, but we know with static friction forces that there's a maximum amount you can have, right? The static friction maximum is equal to that static friction coefficient times the normal force between the surfaces. So what's happening in this problem? Well, essentially that top block is going to be limited in its maximum acceleration because the only force that could supply that acceleration is itself limited. And so we're only going to be able to pull on the bottom block a certain amount. So the problem makes sense to me. Okay, now that we understand that, let's move forward. Typically, we start with the diagram, but we've already got that. The next thing we need to do is define a coordinate system so that we can start defining some unique variables. Well, choosing a good coordinate system typically means aligning it with the most stuff we can. And in this problem, I only see horizontal motion, and I only see horizontal and vertical forces. So we probably want to align our axes with the horizontal and vertical, and I'll just call those the x and y axes. So a y-axis up and an x-axis towards the right. Now that we have our axes, let's define the variables we're going to need. Well, the tension T is already defined for us. Let's create some variables for the masses. We'll let the lower block here be M1 and the upper block be M2. I'm going to do this problem entirely symbolically until the end and then plug in my answers only at that point. We also have two friction coefficients we need to deal with. Now, the static friction coefficient applies to this surface right here. So I'll call that mu s. And between the lower box and the table, we have a kinetic friction coefficient. So I'll call that mu k. Okay, so the only other variable we might need is an acceleration. So I'll call it ax for our x acceleration. No need to be more specific than that in this case because, again, we want these boxes to slide together, which means we don't need an ax1 and an ax2 because they need to be the same. Okay, so we've got our diagram, we've got our coordinate system, we've defined all the variables that we can see that we're going to need so far. The next step is typically to set up a free body diagram for each of the objects that we need to consider. So let's go ahead and do that. It looks like we're going to need a free body diagram for the lower box and the upper box. So I'll put the upper box here, and we'll say he has a mass of M2, and the lower box can go here with a mass of M1. Now, what forces act on each of these boxes? The first one, not to forget, is the weight. Every object, at least on the surface of the Earth, has a weight acting on it. That's going to be directed straight down. It'll be an M2G for the M2 box and an M1G for the box on the bottom. Now, let's go ahead and throw the tension force T, which acts to the right on the bottom box. And there needs to be some force holding the bottom box up. That's going to be a normal force, and it's coming from the table. I want to call that N1 because I can already see that I'm going to have another normal force, and I don't want to get those confused. For the time being, let's go ahead and hop back over to the top block because I can see that there's a normal force holding that block up, and we're going to need to call that N2. Now, notice that normal force on the top block is coming from the bottom block. So if the bottom block is pushing up on the top block, then the top block must be pushing with the same force, just in the opposite direction, back down on the bottom block. That's Newton's third law there. So what left? We still have the friction forces that we haven't dealt with. So there's going to be a friction force on the top block, and that's going to be static friction because those surfaces or those blocks aren't moving relative to each other. They are moving, but not relative to each other. And if that top block is going to accelerate to the right, that friction force better be pointed to the right. So I'll call that Fs for the static friction. Now think about which object is exerting that static friction force on the top block. It has to be coming from the bottom block. So again, Newton's third law, we need to have that static friction force acting back on the bottom block. And this is going to be the step that so many students miss. They're going to forget that action-reaction force back on the bottom block. What's the only thing we've forgotten? The kinetic friction on the bottom block. So I will call that Fk. Okay, and that's got to act back to the left because let me grab a different pin here. If the bottom block is going to be sliding to the right, friction always opposes motion. And so the force that the table exerts on the block is going to be back on towards the left. Okay, so that looks to be our free body diagrams. Now, before we jump into a bunch of algebra and potentially make mistakes and have to redo the whole thing, we probably want to be sure, as we can be, that our free body diagrams are correct. Make sure that we haven't missed any forces. So 2 ways to do that. One is to basically re-go through exactly what we've just thought about and make sure we didn't just miss a force. And you should do that. The other thing we should do is we should think very carefully about each force, make sure we understand on what object it acts and from what object that force is coming from. And we want to use Newton's third law to check that every force which should show up with an action-reaction pair does, and every force that doesn't show up with 2, so that we see both the action and the reaction pair. Every force that only shows up once, we want to understand why. So, looking here, let's see. Let's start with our action-reaction pairs. We've already talked about them, but 2 of them are this Fs to the left on the bottom block and to the right on the top block. We've already talked about how those are action-reaction pairs. Also, the normal force N2. That's the bottom block pushing up on the top and the top pushing back down on the bottom. Now, what about all the other forces? They only show up once each. Why is that? Well, Newton's third law tells us that every force is going to have an action-reaction pair. So where do these have their pair force? Well, the tension force that's applied to the bottom block is coming from the rope. Why doesn't it show up twice? Well, because we didn't draw a free body diagram for the rope. So there's no way for it to show up twice. Also, the normal force N1, that's coming from the table. And we didn't draw a free body diagram for the table. Here's a tricky question. Where would the action-reaction pair to both of the weight forces be? The most common answer students are going to give is they're going to say it's the normal force. And the reason they're thinking that is because, yes, they are equal and opposite forces. But for one thing, an action-reaction pair can never show up on the same free body diagram because Newton's third law tells us if object A exerts a force on object B, then object B exerts the same force back on object A. Notice what I just said there. We're talking about a force on object B and a force on object A. An action-reaction pair can never show up on the same object, and so it's not going to be on the same free body diagram. In the case of the weights, think about what force is actually pulling down on these objects. It's the Earth. And you might not like to think about it, but those objects are pulling up on the Earth with the same magnitude force, that action-reaction pair. You don't ever have to think about that because the Earth's so massive that that doesn't really matter. You're never going to be able to measure it. It's certainly not going to matter for our problem. But we didn't draw a free body diagram for the Earth, so it makes sense that both of those forces as well only showed up once. Okay, let's move on. In a sense, the physics is pretty much almost done now. The only thing we need to do is write down our F equals ma equations and fill them in, and after that, it's just algebra. In our case, we're going to need to use F equals ma on both blocks, and we're going to need to use it in both the x and y directions. So if you're ever lost and you don't know where to go from here, just start writing down the equations that you know should apply, fill them in, and then go back to the problem and ask yourself, which variable do I need to solve for? And then just use your algebra and do it. So let's start with the top block. The block, we called this block 2. Block 2. Okay. Let's start with the sum of the forces in the x direction. Well, that's going to equal max according to Newton. And I'll go ahead and say the sum of the forces in the y direction equals may. I highly recommend that you just write down every physics equation you're going to use in its general form first. And there's a couple reasons for that. One is that it helps you fill in vertically downward and avoid making mistakes. Number two is it reinforces the idea that we're applying essentially the same small number of concepts to every single problem, even though these problems might seem on the surface to be very, very different. And by writing down the formulas that you're using each time, you're going to help yourself understand physics as, a single underlying thing rather than little tools you have to memorize for each individual problem. So now that we have these two F equals ma equations written down, let's start filling them in. And to fill in the left side of F equals ma, assuming you've got your free body diagrams correct, the only thing you need to do is look at those free body diagrams and your coordinate system. Okay, so let's fill in the sum of the forces in the x direction then. Well, in this case, there's only one, and it's the static friction Fs, and it points to the right. So it's going to be positive, equals m. And now the mass, though, be careful here, don't just write down m, because it's the specific mass m2 in this case of the top block, m2. And ax, we don't know what ax is yet, so we'll leave it alone. The sum of the forces in the y direction then. Well, we have an n2 pointed upward and a minus m2g because the weight is going downward. Again, I'm filling this in by looking at my coordinate system here, right? It's relative to the coordinate system I've defined, my accelerations, my forces, everything. Okay. So that's the forces for that one. What about the may side of that equation? Well, the y acceleration in this case is going to be 0 because this box is not moving in the vertical direction. If it was, it would be because it's too heavy and it's broken through the top of this table, or it's bouncing off the table or something. So the acceleration in the y direction is 0. I'll go ahead and take this one step further because it's right there in front of me. This means that the normal force N2 is equal to m2g. Be very careful in problems. You're going to often see a normal force equals to mass times gravity, but not always. In this case, it was true because the acceleration was 0 and because there are no other forces acting in the y direction. But it's perhaps one of the most common mistakes that physics students make is they don't write down their general equation. They don't specifically plug into each side and see what happens. They just assume that the normal force is equal to mg, and they make a big mistake. There's at least 3 big ways that happens. One, we already talked about, is when the acceleration is not actually 0. 2, we also talked about, that would be when there's another force in the y direction. And 3 would be when you're on a ramp or something like that, so that the normal force is not pointed in the opposite direction to the weight. Okay, so that is going to take care of block 2 for us for right now. We'll come back to him later. Let's move on to block 1. Okay, so same thing. We're going to apply F equals ma, which means applying it in both the x and the y directions. In this case, the y acceleration is going to be 0 for the same reasons as we had before. And I'll fill in the x side of the x version first. So I've got a positive tension, a tension to the right, so it's going to be positive. And I've got static friction and kinetic friction acting back to the left. So a minus Fs minus Fk equals max. Okay, and I'll leave that alone. All right, how about the y forces? Well, I've got an N1 pointed upward an N2 pointed downward, and an M1G pointed downward, so those will be minus. This equals 0. Let's carry that a step further, and I'll solve for N1. Pulling the N2 and the M1G over to the right side of the equation. And I can actually take it a step further because I already figured out what N2 equals. It just equals M2G in this case. Sorry, I have an N2 there. That should be an M1. Okay. So that means N1 equals M2G plus M1G, which I can pull a factor of G out of there and write it more simply as M1 plus M2 times G. Okay. And I'll put a circle around that because that looks like something important that I'll need to come back to later. At this point, we probably want to remind ourselves what it is we're trying to solve for. And if you remember, it's this maximum tension force. We're looking for this guy right here. We want to figure out how to maximize him and figure out what his maximum value is. Let's go ahead and solve for him, or isolate him, by moving the static friction and the kinetic friction over to the right-hand side. So the tension then equals M, let's see, I forgot a subscript on the M here. This should actually be an M1. M1AX plus the static friction plus the kinetic friction. Okay, so how do we maximize the tension force? Well, we're going to need to maximize the acceleration. And that acceleration shows up back over here as well. So, and that would be the acceleration on block 2. Well, how are we going to make that acceleration as large as possible? Well, we're going to need to make the static friction force as large as possible. That's actually a good thing because we have a formula for the maximum static friction allowed. That is static friction max equals mu s times the normal force. Which static friction and which normal force would be the next question. And the answer is, well, you pick the two that are relevant to the surface of contact that we're talking about. And right now, the static friction refers to the interface right here between the two blocks. So we want the normal force between those surfaces and the static friction force, or the static friction coefficient. So that would be static friction force is going to equal mu s times N2. N2 is the normal force between those two blocks. And that's going to equal M2AX. And N2, again, we already found it. It's right here. It happens to equal M2G. So we get mu s M2G equals M2AX. I can cross a factor of M off from both sides, or you could think of that as dividing both sides by M2. And we have that AX needs to equal mu s times gravity G. Okay. Keep that in mind, and also keep in mind that what we also just found was the static friction force was this right here without the M2 crossed off. We're going to need that because static friction force shows up right here in our T equation. AX shows up right here, so I'm going to need both of those. The only thing left that I need to go find then is this kinetic friction force. The kinetic friction acting from the table on that bottom block. Well, luckily, we have an expression for that as well. A kinetic friction force, let's start in orange here. Kinetic friction force, Fk, is going to equal mu k times the normal force. And that normal force for us is not going to be N2 because that was between the top and bottom block. We want the normal force between the bottom block and the table, which is actually this N1 right here. So the kinetic friction force is going to equal mu k times N1. And we already solved for that. He's right here for us. I told you he was going to come back in a second. And we get mu k M1 plus M2 in parentheses times the gravity G. Okay. Now we should have everything we need to plug into that tension equation there. Okay, so let's take this guy and plug into him. I'll make a little space for myself over here. Tension equals m1 times ax. But ax we want to write as mu s times g. And then we have plus the static friction force. We also have that over here. He was mu s m2g. And the kinetic friction force we just found, that is mu k m1 plus m2 g. Okay, now let's simplify. Well, let's see. I could pull out of the first two terms a factor mu sg, and that would give me m1 plus m2 mu sg plus, and that last term looks very similar, m1 plus m2g mu k, which I could rewrite as tension. I'll call it the tension maximum here, since that was what we just found. And m1 plus m2 g mu s plus mu k. All right, that is our final symbolic answer. And to get our actual answer, numerically, we would just plug in the values that came along with the problem. Well, the two masses were 20 kilograms and 5 kilograms. So numerically, our answer would be 25 kilograms times 9.8 meters per second squared. And our coefficients of friction were 0.7 for the static and 0.3 for the kinetic, which is going to add to 1. So really all I need to do is multiply 25 by 9.8, and I get an answer of maximum tension of 245 newtons. Okay, so numerically we're done with the problem. But what we should always do is we should go back, we should interpret our symbolic answer, we should make sure that it makes sense. And if we want to be really good, we should think about what happens as the variables increase or decrease. What happens to the output? What variables does it not depend on? What variables does it depend on? What happens if we take extreme circumstances? Like what if the friction between the table and the box goes to 0? Or what happens if the friction between the two boxes goes to 0? We should also look at our symbolic answer if that's all we have, and check to see if the units work out correctly, which we already actually did by finding the numerical answer. But you normally would do that. Okay, well, let's look at it. As either M1 or M2 increases, the maximum tension should increase. As gravity increases, the maximum tension should increase. So if you do this on a planet with stronger gravity, you could pull with a harder force. And as the friction coefficients increase, our maximum tension should increase. You should go back and look back through the problem and see if each of those behaviors make sense. You've probably seen by now a number of situations where the mass actually doesn't matter to the end of the problem. So it would probably be a good exercise to go back and see why it does in this case. Let's also talk about those extreme situations. What about what happens when the kinetic friction coefficient goes to 0? Well, this is like making the table frictionless. And one thing you could do is you could go back and for extra practice on your own, it would be a good exercise, and rework this problem, but say that there's no friction between the table and the lower box. It would make the problem easier. Going back up here, it would change your free body diagrams a little bit. It would eliminate that kinetic friction force right there. But other than that, the problem should stay the same. And if you do that, what answer had you better get out at the end? Well, you better get an answer that's consistent with what we just found, which if we let the kinetic friction coefficient go to 0, you would just be left over with m1 plus m2 in parentheses times g times mu s. So it's not a bad exercise to go back and make sure that's what you get. And in a sense, this is just a more general version of the problem than that one without any friction. Here's another one to consider. What happens as the static friction between the two boxes goes to 0? Well, at first glance, you might think that something's wrong, because if we look at what happens to our equation here, we would still be left with a maximum tension equal to M1 plus M2 G mu K. Now we're saying maybe now there's friction between the table and the bottom box again. So mu K is not 0. And you might be thinking, wait, if we don't have any friction on the top block, there's no static friction on the top block, then it can't accelerate. So if we apply a force of tension to the bottom block, isn't it going to pull it out from under the top block? I'll let you pause the video here and try to think through that and see what the paradox is. I'll give you a hint. Go back and look at how the problem started. Okay, if you've done that, you might have realized that if we look back up here, if we set the static friction coefficient to 0, that gets rid of these two forces. And now if we look at this free body diagram, there is no force in the x direction, therefore there is no way for there to be an x acceleration. But this problem started out, the two boxes were already sliding together at the same velocity. And if we look at the free body diagram for the bottom block, there is still a force in the negative x direction, Fk. And so if the top block cannot have any acceleration, the bottom block better not have any acceleration, which means the x forces need to be balanced. So we're going to find that the tension force is going to need to be precisely equal to F subscript K, so the kinetic friction force acting backwards on the bottom block. Now, maybe the reason this answer down here seems surprising is because we called this the maximum tension. And in a sense, it still is. It is the maximum tension. It's just also the minimum tension in this case. You need a specific, precise value of the tension in order to keep the top box perfectly situated and moving together with the bottom box in this case. Okay, I hope that helps. I will see you in the next video.